Hey there, welcome to another video. In this video, I'm going to show you how to convert from polar to rectangular coordinates, and the next video from rectangular to polar. Converting from polar to rectangular is a little bit easier, it's a little bit nicer. We'll see that right now. But let's talk about exactly how in the world we do this. Hopefully you remember how to even graph these polar coordinates, so that what a polar coordinate really does, it gives you r comma theta. It gives you a distance from something that we call the pole along an angle with a polar axis that this point creates with the polar axis along some sort of array. And so all of our polar coordinates are r comma theta. Now, that's great, but sometimes we actually do like to see rectangular coordinates. I mean, we're really used to it. Rectangular coordinates are x comma y. So, is there a way to get from here to here? Yeah, if I'm doing a video on it, there's going to be a way to do it. So how do we do that? If we understand what this actually means, that r comma theta is a distance from the pole along some sort of angle that we create with what acts as an x-axis, like a polar axis, then we can create a triangle. So if this is our theta from our polar coordinate, and this is our r, distance from the pole, then what if we draw a perpendicular right down to that polar axis? Then if we superimpose this on an xy coordinate system, this distance at that point would just be y. And this distance to where that point would fall on that x-axis would just be x. Now, I hope that you see the beauty in this, because our right triangle trigonometry is going to make it very easy to convert from polar coordinates into rectangular. So we thought polar just means r comma theta, distance from the pole along some sort of an angle. Let the angle be superimposed on the xy coordinate system. That point will have a certain vertical distance, it's y. That point will have a certain horizontal distance, that's x. Let's use our trigonometry. What in the world would we know? Well, we know sine, cosine, and tangent. So what sine would do, sine would take sine of whatever angle we have equals opposite over hypotenuse, or sine of theta equals y over r. Cosine of theta is always the adjacent over the hypotenuse, or x over r. And tangent of theta, just from our right triangle trigonometry, is opposite over adjacent, or y over x. Man, we've seen this for a really long time. Now think about what's going on here. We want to somehow take what we know about r and theta, take what we know here and what we know here, and solve for x and y. But wait a minute. Do you see y and x can be solved for right here? If we just multiply this equation and this equation by r on both sides, we're going to end up with y equals r sine theta and x equals r cosine theta. This is all you need in order to convert from polar coordinates into rectangular coordinates. This is it. All you got to do is find your y and your x. Put them in the correct order, of course, x comma y. But look at what you're given. If you're given a polar coordinate, well, then you have r and you have theta. So you would have r here and you would have your angle here. All we've got to do is take r times sine of the angle they give you, r times cosine of the angle they give you, and that will solve for y coordinate and x coordinate respectively. That's all there is to it. Use these, and only these, to convert from polar to rectangular. They give you everything you need here to plug in here and find this. That's great, we're going to practice that. So what does tangent do? Tangent is 1/2 of the way you convert from rectangular back to polar. So if tangent theta equals y over x, then the angle, so notice you'll be given y and x in a rectangular coordinate and tell you like -2, 3 or something. You'd be given this. You want to find the angle. How would you do that? Take tangent inverse. This is how you'd find the angle if you're given rectangular, right here, y and x. You can put them in a ratio, y over x, take tangent inverse, it will give you your angle. Now, this is a little tricky because our quadrants can get a little bit messed up. We have to really watch this. But you might be also thinking, where's the r come in? Well, because this also does create a right triangle, Pythagorean theorem works. X squared plus y squared equals r squared. Leg squared plus leg squared equals hypotenuse squared. You can do that. And so if you took a square root on both sides, we would end up getting r equals the square root of x squared plus y squared. And you're probably wondering, where's your plus and minus? This is why the quadrants have to be taken into account when you're doing rectangular into polar, because without that negative r, we can be in the wrong quadrant. If you want to use negative r, you can, but most of the time it's easier to find a different angle than it is to deal with a negative r. Long story made short is, this is how you convert from polar to rectangular, and this is how you convert from rectangular to polar. Polar to rectangular is a little bit easier because you don't have to really worry about switching quadrants. This can be a little tougher because we typically keep positive r and adjust our angle to fit the quadrant that our rectangular coordinates were in. So find coordinate first, do all your work to figure out your polar, and then locate if that's in the correct quadrant, switch your angles if you have to. So I'm going to write this out that this is for polar to rectangular, this is for rectangular to polar. We'll talk about all this in the next video, so we'll talk about how you can find the quadrants of your x-y coordinates, that ordered pair, and then we can use that to determine your polar coordinates. It's not too bad, it just requires a little bit more work. Right now, I want to focus on how we can change from polar to rectangular. We'll still identify quadrants. I'm going to use this to do it just to make sure we're in the right place, and then we'll do the math pretty quickly. Again, it gives you everything you need. All right, let's try a few examples, just converting some polar coordinates into rectangular coordinates. We've already seen that it's not too bad. As long as we're given polar, we can identify the r, or the radius really, and the angle that we make with the polar axis, so this theta. And according to that, we know that because sine theta equals y over r, y equals r sine theta, x equals r cosine theta. So here's the process going through it. Number one, we're going to take a look at our polar coordinates here, identify the r and identify the theta, really write it down. That way, when you're converting to x and y for our rectangular coordinates, you know exactly where to look. So when we take a look at this, r is always first in polar coordinates, so r is 4 here. And our angle is 3 pi over 2. Once we've done that, think about what quadrant we're in. Now, it's not such a big deal from polar coordinates to rectangular because we're never going to make a mistake on what quadrant this actually has. But going from rectangular to polar, that does make a difference. And the reason why it does is because tangent inverse only gives you back angles on quadrants 4 or 1, negative pi over 2 to pi over 2. So if something is actually in quadrants 2 or 3, we have to manipulate it. That doesn't happen here, but it's good practice to get in just to check your work to make sure you're there. So if we think about an angle of 3 pi over 2, all the way right there, and a radius of 4, or an r of 4, that's 1, 2, 3, 4. We are actually right on the negative y-axis. So we know that this is kind of a quadrant angle. So we're not in a quadrant, we're on one of our quadrant angles there, so we should end on the negative y-axis. If we don't, we've made a mistake. It's a great way to check your work. So now that we've got our r is 4, our theta is 3 pi over 2, all we really have to do is find x and y. It doesn't really matter which order you do it in, so I'm going to start with y. Y equals r sine theta. So if our r is 4, and our theta is 3 pi over 2, we're just going to look at a unit circle, or your calculator, whatever you really need to do this. Sine of 3 pi over 2 is negative 1. So 4 times negative 1 is negative 4. x is found really similarly, but instead of using sine, we're going to use cosine. That should make sense. Sine was really always associated with a y type of idea, y over r. Cosine is always associated with an x idea, x over r. So if we take our r of 4, and cosine of our angle, so r cosine theta, cosine of 3 pi over 2 is 0. The x-coordinate of that angle is 0. Times 4 is still 0, so x is 0. If we put that together, just make sure you do it in the right order. It's not -4, 0, it's 0, -4. Remember, we're converting from polar, which is always r theta, into rectangular, which always is xy. So this is 0, -4. Now, the reason why we talked about the quadrant was so that you check your work. 0, -4 is you go over 0, you would go down 4. Hey, that's on the negative y-axis. These both refer to the exact same point. It's just a different way to get there. Polar says, find me an angle and then go a distance out from that. And rectangular says, use an x and use a y to rectangularly get to the same exact point. That's just about it. We're going to practice a few more, but this really kind of shows you what you'll be doing to convert from polar to rectangular. Let's try this one. So we have a point in polar coordinates that we want to change to rectangular. The very first thing we're going to do, if we know we're in polar coordinates, is give the r and the theta. R is always first in this ordered pair. So r is -2 and our theta is 0. After that, we're going to look at the quadrant. So -2, 0 in polar coordinates means your angle is 0. So we're really on the polar axis, but -2 means we're going this way. So we'd say, hey, we're not going up, it's not positive, it's not negative, it's at 0. But -2 is 1, 2 positive, but this way would be -2. So we're really over here. It's on this negative x-axis, so it's another quadrant angle, really. Let's see if the rectangular coordinates give us the same thing. In order to convert, we just need to know r and theta. We've written it down so that we're sure what they are. Find x or y in any order that you want. It doesn't really matter. Some people like finding x first because they know to put that first in the ordered pair for rectangular coordinates. That's fine. So x is given by whatever your r is, cosine of whatever your angle is. So cosine of 0 is 1. You find out unit circle, you memorize it, use a table. Cosine of 0 is 1. 1 times -2 is -2. Now notice something. You don't have to worry about what quadrant you're in with polar because these negative r's and angles tell you precisely where you're at, and those signs really do translate into rectangular coordinate system very, very well. So there's never really a confusion about what quadrant you have. We're just going through it to make sure that we haven't made any mistakes, really checking your work. So -2 times 1 is just -2. We do the same exact thing for the y-coordinate, but we're using sine because sine relates to our y. Sine of 0 is actually 0. So -2 times 0 is 0. The y-coordinate here is 0. And so we get this point, -2, 0. Think about where that would be on the rectangular coordinate system. -2, 0 is on the x-axis you go -2, on the y-axis you go 0. This is exactly the same point. Now, hopefully you see something interesting. These are the same numbers, but they mean something completely different. In polar coordinates, this means the angle, which was 0. This means the distance from the pole in the opposite direction of positive r, which would be this way. This means you go left 2 on the x-axis and you do not move on the y. It's going to give you the same point, but they do mean different things. This is rectangular, that's polar. Let's take a look at this example. So we have a point in polar coordinates 6, 150 degrees. Think about what that means. These polar coordinates, or these points in polar coordinates, are always ordered. That means the r comes first and the angle comes second. So let's write that out. The r has to be 6 here, and our angle is 150 degrees. I gotta throw some degrees at you eventually. So we're gonna write that down. After that, we're gonna determine the quadrant of that point. Now, even though polar coordinates into rectangular will always maintain the quadrant, it's not to worry about that. It's so that we can check our work. So let's think about what an r of 6 and an angle of 150 degrees actually means. From our polar axis, 150 degrees positive, is the same thing as 5 pi over 6. So we're going right to there. And because the r is positive 6, along that ray, we go 1, 2, 3, 4, 5, 6. We'd be right about there if each of these concentric circles represents 1 unit. We'd be right exactly there. Now, it's not to graph this point, even though that's very useful and it's great practice to be able to go 150 degrees and out positive 6 for r, but we're getting a quadrant of 2. Now, here's what that'll let us do. When we finally figure out our rectangular coordinates, it better end up in quadrant 2. If not, we've made a mistake. So this is simply to check your work. We know this point is in quadrant 2 if we were to superimpose this on a rectangular coordinate system. Therefore, the coordinates we get has to match that. After that, it's really a matter of using the right trigonometry for the right point. If x relates to cosine, then use cosine to figure out x. We're just going to take our r of 6 and cosine of our angle, which is 150 degrees. Cosine of 150 degrees, or 5 pi over 6, is negative x, square root 3 over 2. If we simplify that, we'll get negative 3 square root 3. The y-coordinates found really similarly, but we're using sine because sine relates to y. So 6 times sine of 150 degrees. Now, because sine of 150 degrees, or 5 pi over 6, same thing, is 1/2, we'll end up with 6 times positive 1/2. Remember, at 150 degrees, that y value is positive. So if we put this together, remember that x comes first, y comes second, put them in order. We're going to get negative 3 square root 3 comma positive 3. Now, I almost did something there that the quadrants would have caught. Let's say, for instance, I had accidentally reversed this and got 3 comma negative 3 root 3. If I had done that, positive 3 comma negative 3 root 3 would have been quadrant 4. I would have looked here and said, wait a minute, this 150 with the r of 6 is in quadrant 2. I accidentally got something in quadrant 4. That does not work. And so I know I would have made a mistake. The way I have it, if I've put this x and y in order correctly, negative 3 square root 3 is, okay, that's left, that's a negative x value. Positive y would give us something in quadrant 2. Quadrant 2 matches quadrant 2. These represent the same point, but using different coordinate systems. This is polar and this is rectangular, but it's giving you the same point. What's nice is these also go pretty quick. So we only have like 4 more to do. It'll just take us a couple minutes, honestly. Let's go ahead and convert this to one. I want to give you some negative r, some negative radius, so that we can get pretty used to it, especially in identifying the quadrant. That's pretty important. When we're just going to go from rectangular into polar, we won't really be using negative r. They're just a lot easier to deal with if we use positive r, but we will have to manipulate some angles. So we're going to practice that now, getting used to where these go. That way we can sort of fix that problem in the next video. So if these are polar coordinates and we are given this by r theta all the time, the first thing we do is identify our r. Our r is negative 2. Now, there's no worry going from polar to rectangular. These negatives will work themselves out to be in the correct quadrants for your rectangular coordinates. We just want to make sure that we nail it the first time and understand what quadrant this point is actually in. So this point in polar says you've got an r of negative 2 given by an angle of 3 pi over 4. Spend just a second and figure out what quadrant that's in. So positive 3 pi over 4 for an angle says from our polar axis we're going 1, 2, 3 pi over 4, that's right here. So here's our ray that we just created, but we're going negative 2. So along this ray in the opposite direction is going to put me along 7 pi over 4, really, or negative pi over 4, but opposite direction from positive r along that ray would be right down here, 1, 2, so negative 2. That puts us squarely into quadrant 4, so I'm thinking quadrant 4, I'm going to write that down. So quadrant 4. Figure out x and y the same way. So x relates to cosine. So negative 2 times cosine of 3 pi over 4. Cosine of 3 pi over 4 is negative square root 2 over 2. Notice also, I've kept the negative r. This will work itself out. You do not have to worry about it. The y value, the y coordinate, is going to be given by negative 2 sine of 3 pi over 4. Which, when we simplify, figure that sine 3 pi over 4 is positive square root 2 over 2. Simplify our 2, so we get negative square root 2. Putting this together in the right order is important. We have x comma y. That's positive square root 2 comma negative square root 2. This should be exactly the same location of this point according to rectangular coordinates. Well, let's see. Let's see if it's at least in the right quadrant. This was in quadrant 4 because we went positive 3 pi over 4 and negative 2. Put us from quadrant 2 into quadrant 4. This says go positive square root 2 and down square root 2. So along the x positively, along the y negatively, that puts us into quadrant 4. So our quadrants match. This is exactly the same point, but according to a different coordinate system. Let's come back. We'll do 3 more and then we'll be done. Okay, moving on, we've got another point in polar coordinates of negative 3, comma negative pi over 3. Every polar coordinate system is in the same manner. We always do r, we always do theta second. So r is negative 3, we're going to write that down, along with negative pi over 3 for our angle. Now let's take a look at that. Negative pi over 3 says from your polar axis, you're going to go, well, clockwise really, pi over 3. That's the same thing as 5 pi over 3, but you got there in a different way. We went down here. Then negative 3 said, yeah, you'd go along that if you're positive, but if you're negative, you're going to reverse right across that pole, like basically reflect that. And you're going to, or add pi or subtract pi, you're going to be in quadrant 2, essentially like you went to 2 pi over 3. So this point is in quadrant 2. If we were to put this on an xy coordinate plane. Now we're going to figure out x and y exactly the same way. So for x, because x relates to cosine, we have negative 3, that's our r. Always r first with the sign. It'll take care of where this is located on the quadrants. We're just going to make sure that we haven't made a mistake by matching our quadrants up. Cosine for x, sine for y. So cosine of negative pi over 3. You can use your unit circle and do this. You can think of this as 5 pi over 3. Either way you go, you're going to get positive 1/2. You could also do something like this, though, just so we don't forget this. Remember that cosine is an even function and sine is an odd function. So you could really say, hey, because cosine's even, I can change the sign of my argument without changing the sign of my function. Opposite inputs have equal outputs. So this is the same thing as negative 3 cosine positive pi over 3. Now, don't do that before you've identified your quadrant, though. Do this in a certain order. So always your r, always your angle without changing it, always your quadrant without changing it. But when you do your math, you can rely on some of these identities we've talked about. But you gotta find this first. So because cosine's even, you can do that to figure out the value, the x coordinate of that angle. So cosine pi over 3 is positive 1/2. Cosine of negative pi over 3 is positive 1/2. So negative 3 times positive 1/2 is negative 3/2. Now, sine is an odd function. And so if you want to figure out sine of negative pi over 3, you could certainly do it by thinking of 5 pi over 3 or negative pi over 3 on a unit circle. You're going to get negative square root 3 over 2. You could certainly do that. You get negative 3 times negative square root 3 over 2. It'll give you positive 3 square root 3 over 2. positive 3 square root 3 over 2. You could also at this point, since you've already written this down and you're not going to change it now, you could change this by its odd function into negative sine of positive pi over 3. Opposite inputs give you opposite outputs for negatives. So I'm going to show that just to refresh your memory. Odd function, change the argument, change the function. This will give you positive 3 sine pi over 3. Because sine of pi over 3 is square root 3 over 2, we're going to end up getting 3 square root 3 over 2, exactly what we would have got if we looked up sine of negative pi over 3, but for some students it's a little bit easier, and I wanted to make sure you remember about those odd functions. Either way we go, though, we now have an x-coordinate, we have a y-coordinate, we can put this together, and this will be the rectangular coordinate way to represent the exact same point. Now all we've got to do is make sure the quadrant is right so that we haven't seen any major mistakes here. If our x value is negative 1.5, that's x is negative 1.5, y is positive, that puts us right in quadrant 2, exactly where we thought. This is just a different way to represent the same exact point. They're both in quadrant 2 at the same exact spot. Okay, in the last two examples, I really want to focus on what you need to be doing if we don't have things that are on our unit circle, like negative 3.1 comma 182 degrees, something kind of strange. Like we can't really look that up very easily, and so you'll be using your calculator. That's perfectly okay. But we do still want to be good at locating what quadrant this point in polar coordinates is, and then making sure that this matches that. So this is a point in polar coordinates. Write down the r first. If it's negative, that's fine. Leave it. If it's a decimal, that's okay too. So we just have negative 3.1. with an angle of 182 degrees. So if we have an r of negative 3.1 and an angle of 180 degrees, notice that if we started from our polar axis here and we went 182 degrees, that's like, just past 180. That's like right here. It would be in quadrant 3 if our r was positive, but it's not. So this goes all the way to 182 degrees, and this is, yeah, but I'm going to switch it up here. I'm going to put you reflected back over here. That would put us in quadrant 1. I hope you see that. 180 degrees is here, 182 degrees is just past that. And we would go out 3.1, 1, 2, 3.1 positively, and this says yes, but you'd go in the opposite direction of that positive r. You would go along this ray in the other direction. That would put you from quadrant 3 into quadrant 1. Now think about this. I hope you remember this. You can always change the sign of your r by adding pi. What that also means is that positive r and negative r are pi radians, or 180 degrees, different from one another. So if you were 182 degrees at negative 3.1, that'd be the same thing as subtract 180. 2 degrees with positive 3.1. This would be at 2 degrees positive 3.1. We did that math already. I'm not going to repeat it, but we were able to change the sign of r by adding or subtracting pi, or 180 degrees. This would be 182 in the other direction, or 2 in the positive r direction. 2 degrees with positive 3.1 as your r. Now, either way you go, you're going to be in quadrant 1. Now we can go ahead and find x and y, but you're going to have to approximate them in order to get kind of useful information here. So x is negative 3.1 cosine, because we have x, 182 degrees, and y is negative 3.1 sine of 182 degrees. If we use our calculator to approximate, we get about 3.10 for x and about 0.11 for y. Why so small? Man, I really hope I put this together for you, but if you have gone 182 degrees and then reverse that because of your negative r, you're going to be floating right above this at 2 degrees, just barely 2 degrees, and 3.1 out. So what's that going to do point-wise for x? That's going to be almost 3.1. It's going to be just under that. So this is 3.1. This is probably rounded up just a little bit, and then slightly above the x-axis. That's what that y tells you. You're just floating right above there. Not very much, just 0.11, because your angle would only be 2 degrees up that polar axis. So does it work? Is this still in quadrant 1? Yes, x is positive and y is positive. It's just barely in quadrant 1, but so is this point. This was just barely 2 degrees up the polar axis and 3.1 units out. So they're both in the same quadrant. They actually represent the same point. This is just in rectangular coordinates, and this is just in polar. Last one. Now, we don't see this very often, but occasionally you'll have some sort of radians that aren't just pi over 2 or pi over 4 or 5 pi over 6 radians, but something like 3.8 radians. It's still polar coordinates, and it's still a point that's written with r and theta, and we're going to write that down. But when you go to use your calculator, because you're going to have to approximate this, a couple things. Firstly, make sure your calculator is in radians, because just like from before, we had it in degrees when dealing with degrees. You're going to want it in radians. Secondly, we really want to understand that pi is 3.14 about radians. And so that will help you determine what quadrant this is in. So we're going to write it down. R is 6. Let's write down 6 for R. And our angle is 3.8 radians. Let's think about that. If pi is 180 degrees or pi is 3.14 radians, because all those pi type units are in radians, then pi stands for 3.14 radians. Where would 3.8 radians end up? Well, it's measured positively, so it'd still be counterclockwise, but we'd go from 0 radians all the way to pi radians, 3.14, and then a little bit past that, 3.8 radians would put us in quadrant number 3 as long as our r is positive. So this says go past 3.14 to 3.8. Somewhere along there, you're going to go from our pole 1, 2, 3, 4, 5, 6 units out. That's what that says, so we are in quadrant 3 for sure. What if it had been negative r? Then you'd go 3.8 radians and you would reflect back. You'd go in the opposite direction of that angle, 180 degrees or pi different, and you'd be in quadrant 1. This one happens to be in quadrant 3. And then we go about finding x and y, so we're still going to do the same thing, but we're going to have to approximate, so make sure your calculator's in radians like we've already talked about. And if we do that, we're going to get 6 times cosine 3.8 radians is about negative 4.98, and y is about negative 3.85 if we use sine of 3.8 radians times 6. So that's going to give us this point in rectangular coordinates. Same point, different way of looking at it. Let's just make sure the quadrant matches. Negative x and negative y puts us right in quadrant 3. This was in quadrant 3, just past 3.14 radians, and positive 6. Quadrant 3 matches. It looks really good. Just a different way to look at the same thing, honestly. So hopefully that makes sense. I hope I've explained well enough how to convert from polar to rectangular, the usefulness of double checking with your quadrants just to make sure you haven't made any errors. This is going to be exceptionally useful when we go the other way around. So the next video is going to talk about what if you have rectangular coordinates for a point, can you get to polar? Yes, but the tangent's a little bit tricky because it can only return angles in quadrants 4 or 1. So if your rectangular coordinates are giving you angles in quadrants 2 or 3, you're going to have to add or subtract pi to get there. We'll talk about it in the next video. Hope this has made sense. Hopefully you see the usefulness and the connection to our right triangle trigonometry, and I'll see you for another video.